Hello everyone, I'm Ding Ching from University of British Columbia. Today, I'm excited to present our paper, Procrustes, a data flow and accelerator for sparse DNA training. This work is collaborated with Amin, Xiaowei, Max, Guy, and Meshko. In short, we perform hardware acceleration for sparse training. But we face two challenges. One is that sparse training algorithm is not hardware friendly, and the other, prior sparse inference accelerators are inefficient for sparse training. To address the challenges, we take an algorithm hardware co-design approach and achieve up to 3.26x less energy and offers up to 4x speedup across a range of models, while pruning weights by an order of magnitude and maintaining the unpruned accuracy. First, we will focus on adapting sparse training algorithms to the requirements of an efficient hardware implementation. Before we dive into why sparse training algorithm is challenging to accelerate, I would like to provide some gentle background. Conventionally, we obtain a sparse model by first training a dense one, and then iteratively prune and retrain to recover accuracy. However, this takes more energy and time compared to a dense baseline due to the additional iterative pruning and retraining procedure. Recent work studied techniques to train a sparse model from scratch to avoid this overhead. However, this is still not hardware-friendly and often inefficient. Here, we prepared a table that compares three sparse training algorithms and their properties. We won't go in depth into the table. The key message is that all sparse training algorithms have some aspects that are not hardware-friendly, which are marked in red. For example, all need sorting to identify important weight connections, an expensive operation not supported in current accelerators. Moreover, two of them prune gradually and another one has no compute sparsity during training. In this work, we choose drawback as a case study and we first adapt the sparse training algorithm to be more hardware-friendly, and later we'll talk about how to develop efficient accelerators for it. Drawback is an algorithm performs weight pruning during training. The core idea is to reinterpret weights. The model's weights can be viewed as the initial weights plus the accumulated gradients, where the accumulated gradients represent the amount of learning. Drawback found that it is sufficient to track a small amount of highest accumulated gradients that account for the most of the learning. Therefore, the accumulated gradients can be heavily pruned provided that the initial weights are always recomputed. However, this is inefficient as no compute sparsity exists during training because of the regeneration of the initial weights. We observe that regenerated initial weights is important during the early training phase to provide a scaffolding for the model to learn, and its importance reduces as the training continues and the accumulated gradient start to dominate. Therefore, we choose to gradually decay the initial weights to create compute sparsity. Our experiment shows that initial weights are decayed to zero in less than 1% of the total training time, and therefore we obtain compute sparsity for more than 99% of the total training period. In addition, all sparse training algorithms require sorting to identify weights to keep. For example, to prune a 75% of a toy 4-weight model, the sparse training algorithm will sort across all weights and prune 3 lowest magnitude weights and only track the top weights. However, exact sorting across the entire model is too expensive. Our observation is that sorting is too strong and we don't care about the relative order inside the tracked and the pruned set. Therefore, a partitioning scheme is sufficient. For example, when new weights are generated, we can maintain a threshold to classify them into the tracked and the pruned set. And the threshold will be adjusted with new incoming weights. We use a streaming quantile estimation algorithm for predicting the dynamic threshold. To quickly recap, we have talked about two algorithm adaptation techniques to make sparse training algorithms amenable to hardware acceleration. One is that we decay initial weights to create compute sparsity, and the other is to replace expensive sorting operation with a cheap partitioning scheme when identifying weights to keep. You may wonder the accuracy impact of the proposed algorithm adaptation techniques. We have trained MobileNet version 2 and ResNet 18 on ImageNet and achieved an order of magnitude weight reduction on those models. Based on our validation curve, we can see that neither accuracy nor convergence time is compromised compared with dense SGD baseline. The takeaway is that our adapted algorithm achieves around 10x compression without loss of accuracy. Now, we have successfully adapted the sparse training algorithm to be more hardware-friendly and energy efficient. Let's switch gears to discuss how to develop efficient hardware accelerators for sparse training. A natural question that we want to ask ourselves is, are sparse inference accelerators efficient for sparse training? The answer is no for the following two reasons. First, sparse inference accelerators typically encode compressed sparse weights linearly, which is bad for training. This is because, for example, during backward pass, it is required to access transposed weights for FC layers and a 180-degree rotated filter for conv layers. Meanwhile, sparse inference accelerators either do not perform load balancing or only take advantage of static nature of the weights in inference and performs software pre-processing. This does not apply to sparse training because weight sparsity is dynamic. In addition, naive load balancing destroys spatial reuse and requires a complex interconnect to recover. Later, we will talk about how to perform load balancing without compromising reuse. To address the first challenges we just mentioned, which is to support efficient sparse weight access across different training phases, we use a variant of compressed sparse block format. A schematic is shown in this figure. We have a weight array that contains all compressed non-zero elements. Besides, we have two auxiliary structures to record the metadata. One is the pointer array that supports flexible interblock access. This is required because weight blocks are accessed in different order for different training phases. The other is the mask array, which contains masks for each block. This supports flexible intra-block access, as we can decode the compressed block differently if we need to access transposed or rotated blocks. The takeaway is that we develop an efficient data layout to support efficient inter- and intra-block access that is suitable for training. In addition, we need to support efficient load balancing for dynamic sparse weights. We illustrate the basic load balancing idea with the following schematic. Assume we have 4 P's where each P fetches some tiled workload, and the latency will be bounded by the slowest PE with the densest workload if PEs are synchronized. To balance the workload, first we cut the workload into halves and detect the imbalance of sub-workload by accessing the metadata with our compressed sparse block format. Then we sort based on the amount of non-zero elements and fold to create sparse dense sub-workload pairs. The most dense one will be paired with the most sparse one, and so on. Finally, the paired sub-workloads will be scheduled on PEs and the workload is balanced among PEs. The takeaway is that we perform dynamic scheduling at finer granularity to balance the workload. However, there are some issues when naively perform load balancing on two-dimensional PE array. And in the next slide, I will show how Procrustes solved them. We will identify the issue with a toy 2x2 PE array. Assume we spatially unroll the input channel dimension across PE rows and the output channel dimension across PE columns. The resulting spatial reuse pattern is the following. Input activations are multicasted horizontally, weights are unicasted, and partial sums are collected vertically. Different subscripts here distinguish different working sets. If we focus on weight working set for now, notice that I use darker color for weight working set with higher density and the light one for the sparse one. The resulting workload variation is indicated on each PE. To balance the workload, we assume we cut the workload in output channel dimension and schedule balanced sub-workload onto PEs. Notice that errors are thinner for half working sets. However, we observe the following issues. For input activations, we find that some PEs are required to buffer double the content and therefore incur additional bandwidth requirements on the interconnect. For partial sums, notice that spatial reuse pattern is destroyed and we cannot collect the partial sum working set within a column like before. The takeaway is that naive load balancing can destroy spatial reuse or requires a complex interconnect that exploits reuse beyond single row or column to recover reuse. In contrast, Procrustes performs load balancing with a modified data flow called spatial mini-batch data flow to fully preserve reuse opportunities. Here, instead of mapping input channel dimension across PE rows, we spatially unroll the mini-batch dimension, which is abundant in training. Output channel dimension is mapped across columns same as before. The corresponding reuse pattern is the following. Input activations are multicasted horizontally, weights are multicasted vertically, and the partial sums are unicasted. Notice that workload variation still exists, and similarly, we can schedule balanced sub-workload onto PEs. This time, we do not incur any overheads. Input activation does not require any additional storage or bandwidth requirements. Weight subtiles can be still multicasted vertically to explore reuse. And partial sum subtiles are unicasted still, so no loss of reuse opportunities. The takeaway is that load balancing with our modified spatial mini-batch data flow preserves reuse, and only need simple one-dimensional interconnects to support multicast and unicast patterns. To quickly recap, we identified two challenges that sparse training accelerators will face. First, we developed a flexible compressed sparse block format to support different sparse weight access order across different training phases. Next, we developed load balancing scheme for the dynamic sparse weights during training. With our modified sparse mini-batch data flow, we can preserve reuse and retain a simple interconnect during load balancing. Our Procrustes architecture is shown here. We use a generic 2D P array architecture with three simple one-dimensional pipeline interconnects for weights, input activation, and partial sums. Additional structure like load balancer and quantile estimation unit is marked in red. Our PE architecture is shown on the right. It consists of FP32, MAC, and some local storage. The additional weight regeneration unit is marked in red. The takeaway is that with the proposed hardware techniques, Procrustes executes highly irregular sparse training with only simple and regular hardware components that avoid additional hardware complexity. Let's have a look at Procrustes simulation result. First, we present the energy result for training ResNet 18 and MobileNet version 2 on ImageNet. PQ, CK, and KN represent activation stationary data flow, weight stationary data flow, and our Procrustes spatial mini-batch data flow respectively. D and S represent dense baseline and sparse accelerator respectively. So ours correspond to these two bars. The breakdown in each bar corresponds to energy spent in forward, backward, and weight update paths. We achieve energy saving across all training phases, and we find that the optimal energy of different data flow is quite similar, so we still obtain energy optimality when switching to a different data flow. Next, we present the latency phase breakdown, which follows a very similar structure. Similarly, ours is here. We find that latency varies a lot for different data flow, and our spatial mini-batch data flow achieved the best because it achieved good PE array utilization and its workload are easy to balance. The takeaway is that we achieve 2.27x to 3.26x energy saving and 2.28x to 4x speed up across all models evaluated in the paper compared with a dense optimized baseline. Lastly, let's summarize what we have learned. First, it is important to develop hardware-aware algorithm adaptation techniques instead of building complex hardware components for algorithm components that are hard to accelerate. Next, it is important to perform load balancing for executing DN workload with irregularity like sparse training. And more importantly, we should develop a load balancing scheme that preserves reuse to avoid redundant access to global buffer and avoid complex delivery pattern that could saturate your interconnect bandwidth. With all this in mind, we achieve up to 3.26x less energy and offers up to 4x speed up across a range of models, while pruning weights by an order of magnitude and maintaining the unpruned accuracy. Thanks for listening. If you want to know more, feel free to check our paper. And if you have questions, please do not hesitate to send me an email.